This PCB is what we have to understand. What is its block level schematic, how does it work, how does it store energy, how is it that I am able to read this bearing temperature, this one's temperature without any battery, non-invasive, no battery, right, and values by magic appear on the dashboard of the automobile driver. I have just taken automobile as an example, but it could also be any workshop, mechanical workshop machine like lathes, milling machines and so on, wherever there are bearings, right, wherever there are rotating components, rotating machines, you will have to have a bearing, and this is the whole focus really about measurement of bearing temperature. Okay, so let us go back and look at this circuit the block level circuit diagram. You can see that we have the rotating bearing here with the neodymium magnet that I mentioned right here. So, this is the neodymium magnet arc, one arc is here, another arc is here, both the arcs are shown here. So, let me rub it off so that we maintain some clarity in the picture, and this is the rotating bearing, this is the bearing which is rotating all the time. Now what happens, when the bearing is rotating, the arc magnets which are attached to it are also in motion, are also rotating, and what actually happens is it induces a small amount of AC voltage across the blue coil that we mentioned, and that voltage that is induced is shifted, is given to a rectifier block. Because there is no center tap, you may want to put a bridge rectifier. Okay, you may have to put a bridge rectifier, and because you are energy harvesting, you want to ensure that the forward voltage drop of this diode, bridge diodes, is as low as possible, as small as possible. So, you would go for Schottky, which would give you a forward voltage drop of 0.3 volts. So, choose Schottky diodes so that you will be able to essentially ensure that you will be able to maximize the amount of energy that is harvested. Now we see another block which perhaps we have never come across, okay, and this is the boost converter, okay. I have written it here, but I will just write it for the explanation purpose. Its business is this, that this microcontroller typically operates at somewhere from 1.8 volts, greater than 1.8 volts, up to about, let us say, 3.6 volts. Now what you get out of this DC here is not this here, not this voltage at all, not this voltage. Now the question is, how do you generate this voltage, how do you generate this, or any voltage greater than or equal to 1.8 to about 3.6, how do you generate this? For that they use this boost converter, which can take anywhere in the range of 200, 250, no, I would say that is conservative, that is being I do not think that will work there, but let me put it 400 millivolts upwards takes 400 millivolts DC as an input and is able to generate 1.8 volts to 3.6 directly, okay. So that is the function of this boost converter. Now this boost converter gives you two outputs, one is called VLDO and the other is called Vout. Just for explanation, let me just rub off everything here and continue the story. I am sure you are making notes about the different components that we have. that we are sketching. So right. So here we have two outputs, one is called VLDO. This LDO actually stands for low dropout regulator. LDO stands for low dropout regulator. Vout is Vout. Vout is what you are looking for, is Vout. Okay. Let us say, okay, so now you have VLDO and Vout. Let us say that you are interested in setting Vout to 2.8 volts, okay, or let me make it even lower. I said there is a range over which it operates. I will take an example. Let us say you are interested in 2.3 volts. I think we will keep it at 3.2, that is better. Okay, you are interested in output voltage of 3.2 volts. So, which means this Vout is now set to 3.2 volts. Okay. Now, this boost converter, moment it has a stable 400 millivolt at the input here, the first output it generates is the VLDO. VLDO, the speciality of VLDO, this is very specific to this chip called LTC 3105. The speciality of this chip is it can't allow you to draw more power. It is a low power output, I would say low power output. I think there is a spec that it should not exceed, you can't draw more than 6 milliamperes of current. So, and typically VLDO can also be set, I think there is a relation between, if you set Vout to a given voltage, VLDO will be of a certain voltage. We will not get into that detail, but still understand at the block level that the important point is this VLDO, you can't use it for high power applications. The whole area of IOTs, design of these embedded systems and all that, when you say high power, we are already talking of high power for us is already in tens of milliamperes. That is the thing. If you say 10 milliampere, that and 10 milliampere and 3 volts is a lot of power for us. So, if you say 30 milliwatts, 30 milliwatt is a lot of power for embedded systems. Whereas, if you say, so I will say, oops, not able to write this properly. If you say 3 volts 10 milliampere is a lot of power, I would say it is high power already, tending to become high power. Whereas, if you say 3 volts and 1 milliampere, then you are still at 3 milliwatts, which is still fine, right. So, the point I am trying to drive at is that this VLDO you can't draw high power. The maximum you can draw, you may want to look up the data sheet for better clarity, is that is about 6 milliamperes. I will not get into the detail of the data sheet at this stage, but I am trying to drive home a very important algorithm that is out here. So what you now do is, moment VLDO is available to you from a stable, let us say 400 millivolt at the input here, this power mux essentially takes two inputs, one coming from this super capacitor and the other coming from VLDO. Obviously, if you put a large capacitor here, the energy storage is going to be slow, is because the plates are very large, the area of the capacitor is large, it has to build up slowly, and at one stable point it will actually come to the set V out of 3.2 volts. However, it is going to take time to reach that set voltage across the capacitor, which would largely depend or only depend on the value of this capacitor, right. So, that is the key point here. So, it turns out that VLDO is the one that will give you V supply to begin with. I hope you will agree. Because VLDO is still coming up slowly, 0.1 volts, building to 0.2 volts, building all the way it has to reach 3.2 volts across this capacitor. So, to reach that point it obviously takes a lot of time, and the fact that it has reached 3.2 volts from this harvested source, this coil and this magnet source, is already good enough to mention that you can actually use it to do something useful. Let us move on. Now that VLDO is the first one to be the output from this power mux, we now switch on the microcontroller, and what we do is we energize the Hall sensor to obtain the magnetic field value, the ADC value which I showed you in the previous graph. So, this ADC here, this is the ADC, right. So, the ADC I showed you some numbers 450, 500 range and all that. So, that number is what you will see here. So, what you do now is you just sense the value of the Hall sensor and store it in perhaps in RAM, for instance. For example, it could be in RAM. Okay. Meanwhile, when the output from the boost converter starts to build up because of a copious energy flow at the input, the boost converter senses that there is sufficiently good input and gives a signal out called the power good signal, power good signal. Let me write it again. Generates the power good. Moment the power good signal comes to the microcontroller, the power mux would have actually shifted from VLDO, which was originally the V supply was equal to VLDO to begin with, now becomes V supply equal to V out. Moment this condition comes, the microcontroller decides that it is time for this high power operations such as computation and communication to go on, and decides to send out a Bluetooth packet, a Bluetooth data packet, Bluetooth data packet, right, Bluetooth low energy data packet. And because the supercapacitor provided sufficient power for the Bluetooth low energy packet to be transmitted, the output V out now falls down. When V out falls down, P good signal obviously reverts to its original status, and microcontroller decides to switch off all power consuming blocks such as radio and itself in fully on state and goes to sleep mode, awaiting the next P good so that it can do a communication. This is the big picture, the block diagram of what is actually implemented on the PCB that we have seen, and essentially all of this means a very important point, and that is that power for embedded devices, power management for embedded devices, energy harvesting, let me write it here, energy harvesting for embedded devices is indeed very important. So, let us capture this bearing temperature measurement into a flow chart, and let us explain this flow chart in clear terms, so that you actually know how an IoT system, IoT device that you want to an IoT product that, or an IoT system that should be doing bearing temperature measuring monitoring, temperature monitoring actually works or actually should be done, can be captured in this little flow chart. So, how do you start? What is the whole process? Let us go back to this flow chart. Essentially what I will do is I have this flow chart here, but I will just recap everything so that it is better for you. The first block indeed is the start block, which you see here, right. This is the start block. After that is this block. This block is the Gpio initialization, right. What does it mean? It simply means that the power good signal, which is like an input to the microcontroller, is configured, that particular input GPIO line is configured as input. Okay. All that activity is actually done in this block, which is the Gpio initialization block. Then what you do? You essentially boot the microcontroller and go to sleep. Okay. Remain in sleep condition for as long as P good continues to be low. In other words, if this signal P good is low, means you can't do anything with respect to communication, and although you could do sensing, okay, because with VLDO output you can actually go and sense the signal, but that is a minor point that you can use VLDO but that is not really completely captured in this little flow chart. So at a high level, if P good is low you go to sleep, and moment P good becomes high you come down, you enable several sensors. You may also want to read the ADC value again if you wish, and you may want to store and check if P good continues to be good. If P good flips to no, goes low, do nothing, just go back and sleep. Good thing you would have done is you would have probably got one value either using VLDO or using the V out, not actually V out, actually the VLDO. You would have read the sensor value and stored it into your RAM. Moment P good continues to be high for a sufficiently long time, you know that the capacitor has charged sufficiently well. This is the super cap in the previous super capacitor is charged, and is now ready for providing a high power for the radio circuit, right, for the radio circuit, so that a BLE transmission is now possible along with the sensor data which was obtained from the Hall sensor into the ADC, analog to digital converter pin of the microcontroller. Soon after a BLE transmission is done, this is done, what happens? The system automatically shuts down because the super capacitor would have depleted significantly below its normal offering of a stable output voltage, pulling down P good again, and the system actually goes back to a cold start situation. This is essentially what is done in this complete in this power management flow chart that I mentioned to you. Let me quickly also show you some energy, something related to the energy harvesting part. This is a picture of the x axis indicating the bearing rotation RPM, okay, and this indicates the energy that we harvested, right, we harvested. Clearly as the bearing speed increases, rotation RPM increases, the possibility to harvest energy also increases. Up to 9 millijoules of energy was harvested from a minimum of about 3.5 millijoules of energy. So a clear indicator that speed of the bearing also is a important requirement to ensure that the whole system can work, can run with harvested energy. In summary, let us go back to this nice picture of this ball bearing system. Bearing rotates, the bearing rotates and bearing heats up due to malfunction sensed by these neodymium magnets. There is a change in magnetic field due to change in temperature caught by this Hall sensor, given away to a microcontroller unit which is essentially measuring the magnetic field. In the process this blue coil here is actually harvesting due to change in magnetic field due to these arc magnets, that is here on this cable here, connected to a rectifier circuit conditioned through a boost converter, power management circuits and boost converter. Energy stored on this super capacitor here, this one, this capacitor here, let me put it here, this super capacitor here and the complete circuit here, which essentially contains a microcontroller and of course the you can see a chip antenna here, right here, which is essentially the Bluetooth low energy antenna here, which in summary means that we did several things, right. We measured temperature indirectly, we also harvested energy, and we actually built a semi IoT system, I would say, which essentially makes a measurement, does some computation, does communication as well. And we call it semi IoT system because we did not get into any actuation part, we did not close the loop, we did not jam the bearing, for instance, we did not jam brakes on the vehicle, or we did not stop the lathe from rotating because we see an abnormal condition for these bearings, we have not done that. So all of that means you must get into deep analytics on the data that you obtain in order to see trends with respect to wear and tear of this such a bearing, and then conclude indeed that it is time to replace these bearing components. Thank you very much on this for your patience, and we will handle power management as the next module in our because we got into power management with this example. Let us start with power management in our next class. Thank you.